Because physics is, at heart, an experimental science, basic principles and ideas are formulated in terms of the experiments that can be performed to illuminate them. The language of experiment is woven throughout physics, and we exclude from physics anything that is fundamentally non-quantifiable. To compare experimental results, it's important to express them in terms of well-defined and common quantities and units. Physical quantities are always, at least in principle, the answer to a clear experimental question. And again, that's in principle. Sometimes you can't do the experiment, sometimes the experiment would be hard or impractical, but in principle, anything you ask in physics should be answerable by an experiment. As quipped by the science fiction author Robert Heinlein, what are the facts and to how many decimal places? I.e., he was saying the only things that are facts are things that can be expressed as numbers. All of the possible types of units taken together constitute the system of measurement. Historically, there have been many. Every locale and people defined their own, and they made sense to those people. Units were often defined by convenient objects available to those people. For example, the foot originally was simply the length of a typical male foot. In fact, it was the length of the king's foot. In an age before industrialization and standardization, this was sufficient, though it was inconvenient when the king died and you had to reorder everything. So we see actually pretty early in the development of nation states, we start seeing laws that say the foot is so-and-so's foot, and even when he dies, it stays that same length, that we have a standard foot. Because it's inconvenient to rescale everybody's height at the time the king dies. On the other hand, in pre-industrialized nations, for the most part, you didn't need super accuracy. The fact that something was off by a little bit, you couldn't measure it that accurately anyway, so it didn't matter. And so it was only sort of as we developed industrialization that it became important to really rectify and standardize these things. In 1789, the French Revolution occurred, and one of its eventual mantras was, "No more kings." Since it was also the height of the Enlightenment, the French decided to make a system based on science rather than people. This is the basis of what we call the metric system, which is more properly known as the System International, or SI. And you'll often hear people in English especially say the SI system, which is a little redundant because the S in SI is itself system, but that's the way language works. Then the armies of Napoleon carried that SI system to all corners of Europe. And then eventually the European powers carried it to wherever they colonized. But when the French were defeated, the newly liberated nations mostly decided to keep the SI system. Why? Because it's expensive to go back and forth, and it's actually convenient to have a common system of measurement. So before Napoleon, nobody would be able to agree on it, but once it had been imposed by force, it was recognized as being convenient to have. And so the countries sort of unofficially just kept it rather than do the agony of going back again. Nature, of course, is indifferent to our choice of system. We can use any system of measurement we want, and physics will still work. It just needs to be expressed in that system. But SI has spread to just about everywhere on Earth, except the United States, Liberia, and Myanmar, the country shown in red on that map. SI has several advantages. The units are defined via experiment rather than human foible. It's international and not linked to any particular country. It's based on powers of 10, making calculations relatively simple. The base units were chosen for human convenience. And all units use the same system of prefixes, so there are few conversions to remember. This turns out to be its overwhelmingly huge advantage compared to traditional systems. The conversions are few in number, and because it's based on powers of 10, they're easy to do. And so it's just a simpler system for that. Nearly all science and engineering today is conducted in SI, and we'll use it for nearly exclusively. Even in the United States, scientists and engineers tend to work in the metric system because they need to communicate with people outside in the outside world, and because it makes so much sense. This doesn't mean that the US system is wrong or immoral, but it is inconvenient in a lot of ways, and so people have gravitated this way. The United States, being its own large internal free trade zone, has not join that. We are a big enough economy to resist that trend, although even now metrification is happening sort of gradually because it is just business-wise convenient to have everybody on the same system. Because it can be inconvenient to carry large numbers in front of a measurement, SI has a system of so-called prefixes that modify a quantity. All the units use the same prefixes. So you've heard some of these. 1 mega is the same as a million, and 1 kilo is 1,000. 1 centi is 0.01, which is 1/100th. 1 milli is 1/1000th. 1 micro is 1/1,000,000th. And 1 nano is 1/1,000,000,000th. And you can actually just replace those numbers with these symbols and vice versa. They have abbreviations. I guess I should have written in here. I did not. So the abbreviations for kilo is K. Different color. And centi is C. milli is lowercase m, micro is Greek letter mu, we'll get to write that a lot in this class, and then nano is lowercase n. And mega is capital M. And you'll see there's already potentially some sort of conflict here because mega and milli both start with M, and so the SI powers that be decreed that if it was more than the base unit, you would use capitals, so a million or a billion or a trillion times the base unit, but if it's less than the base unit, you would use lowercase. You might see that there is sort of a problem with that. The kilo is certainly more than the base unit. It's 1,000 of them, but it's written with lowercase k, and that is for historical reasons. It's not the way we would do it today if we were starting from scratch, but before people had regularized this system, people had already started writing kilometers with lowercase k, and so we just stick with it. We accept it as a sort of unfortunate historical oddity. So we can see here that 15 kilometers, or kilometer if you prefer, is 15 times 1,000 meters, so it's 15,000 meters. And 562 millimeters is 562 times 1/1000th of a meter, so it's 0.562 meters. Again, a use of the metric system that's convenient is that these prefixes work for anything. So just like 1 kilogram is 1,000 grams and 1 kilometer is 1,000 meters, and a nanosecond would be 1 billionth of a second, just like a nanometer is 1 billionth of a meter. In other words, you don't have to learn different conversion factors for all the different things. And if you're familiar with the US system, also called the British Imperial System, then you're kind of used to the idea that if you want to go from inches to feet to miles, it's two different conversion systems. And then if you want to go from ounces to pounds, or ounces to quarts to pounds, say, it's a whole different conversion system. There's no rhyme or reason to it because they were evolved for different purposes. And the metric system is more coherent, not because the people using it are smarter, but because it was literally designed. People sat down and said, how have we been using units? What could we do that were better? So let's take a quick tour of the SI system. The SI unit of length is the meter, symbolized by lowercase m. Its original definition was the length of a specific standard bar. Today it's defined in terms of the speed of light. Even this is a little off. The original definition of the meter was 1/10,000,000th the distance from the equator to the North Pole, which is awesomely both like spectacularly hard science to do and yet in principle a very simple experiment, which is the keynote of all of the French Revolution ones. They were grand experiments that you could do to make these things not tie to people. Why do we not use that? Because the Earth is not really a sphere, it's a spheroid, so you have to specify where. So eventually that has to say like along the longitude running through Paris, and then the Earth's shape changes with time. The Earth's surface moves around, the Earth grows a little bit bigger with time, so this was no longer really a fixed thing. So at some point they're like, well, let's just take its current best thing, take a bar of iridium and make it that long. Why iridium? Because iridium is mostly non-corrosive and is relatively insensitive to temperature changes, so it was easy to say it would stay at. But even then they had to specify, well, at this air pressure with this temperature and so on. It became again very bizarre, and the thought was, well, what if something happened to that bar? Today it's defined experimentally. It's the distance light travels in some ridiculously short amount of time, and the short amount of time was picked to get the meter right the first time, but now we don't define the meter, we measure it, essentially. Not us, we'll just use calibrated meter sticks and so on, but in the world as a whole. If you know the US system, 1 meter is just a little bit more than 3 feet. You can basically convert meters to yards and to be not too far off. The SI unit of time is the second, symbolized by the letter S. It's exactly the same as US second. Originally it was defined by motion of pendulum and then a bunch of different things. It's currently defined in terms of transitions of a certain atomic state, I believe in cesium, where they measure the frequency at which the state oscillates in a certain magnetic field. A kilosecond is about a third of an hour. People don't tend to use kiloseconds or megaseconds. In this case, and only in this case, the sheer historical inertia of people's usages means that we really still have that 1 minute is 60 seconds and 1 hour is 60 minutes, which is 3,600 seconds. The people at the Bureau of Standards, for instance, they're upset with all of us that we still use hours and minutes. We really should be using kiloseconds and megaseconds and gigaseconds instead of minutes and days and years. But we don't. And people are much more tied to their sense of time than distance. The French actually found that out during the Revolution. There was a metric time, a metric second with a metric hour and a metric day and a metric week, and they were all powers of 10, and it fit the system beautifully, and people hated it. And it lasted for about 3 years, and then the French gave up because there was such resistance to using it that the National Assembly just said, we will go back to using hours, minutes, hours, days, and weeks. So we are kind of stuck with that. The only people I've ever heard who routinely work in terms of things like kiloseconds are astronomers. We tend, as astronomers and astrophysicists, tend to do observations in terms of kiloseconds because you're not tied to the day anyway, so it wasn't that hard to do a switch. All right. Mass is defined kind of loosely as a measure of how much stuff is in an object. It's a pretty loose and bad definition. We'll define it more precisely later in this class. It's related to, but distinct from, the weight of an object. Confusingly, countries that use SI often treat mass as weight. This is one thing that the imperial system gets right. So if you ask someone from Europe how much they weigh, they'll say, I weigh 52 kilograms. But they don't weigh 52 kilograms, they mass 52 kilograms. It's actually quite important and different. The British system, the unit of weight is the pound, and it is actually a unit of weight. The unit of mass in the British system is something called the stone or the slug. It's bizarre, nobody uses it. But just accidentally, the British system gets this one right. The SI unit for mass is the kilogram. That's kind of weird, right? We've had the meter and the second, but now we have the kilogram. For historical reasons, we don't tend to work with grams, although chemists really do. 1 kilogram weighs a little bit more than 2 pounds, at least at the surface of the Earth, and we'll talk more about that later in the class because weight will depend on where you ask it. Why is it in the kilograms instead of the grams? Because the gram is a small amount of unit for a physicist. For a chemist, it's a pretty good amount of mass. You tend to add things in multiples of grams or maybe submultiples of grams. But for people, for physicists working with physical objects, large, like tabletop type objects and larger, your mass is in sort of already the 55,000 gram mass, that kind of range. And so it was just convenient to say, let's work with the units people tend to have in front of them. It's a little annoying that the base unit is not actually a base unit, that the unit we use, the kilograms, are not the base of the system, and it could have been done differently. It really is for historical reasons. It comes back to that the original definition, the gram, was in terms of the mass of a certain volume of water. In other words, you took the centimeter, made it cubic, so you made a cube the size of a centimeter, filled it with water, and that would be 1 gram, which is very simple. It's no longer the definition because there's a lot that goes into that that's bad, so we have a different way of doing it. And now we define the kilogram through a kind of bizarre experimental chain. And it just turned out that instead of saying take 10 centimeters on a side and call that the weight, we took 1 centimeter, and it didn't scale nicely for physics purposes, so we use the kilogram. There are actually other units. We haven't talked about temperature. We haven't talked about electron charge. There aren't that many. It turns out you only really need 4 fundamental units to span all the physical quantities that we've ever encountered. But we'll talk more about that later, about the mysterious 4th unit, when it has relevance to us. All right, we often need to convert a quantity from unit to a different one, say from miles to kilometers, or from days to seconds. There are lots of different approaches people take, and you can use any valid one. I want to be very clear here. In this class, we always focus on any valid method is the one to use. You don't have to do it the way that I or the AP committee, quote-unquote, expects you to do it, but just a way that works. And part of this class will be learning how do you tell ways that work from just random things that you do. And we'll talk about that. But you, especially for conversions, you've run into this probably in previous science classes. You've been taught to do it a certain way. If you understand it, do it the way that you've been doing it. I'm going to present another method right now. It's the way I do things, and it makes sense to me, but it is by no means morally superior, and you should just use whatever works for you. But if you have learned converting units and it was troublesome, then this is a way that doesn't seem to be taught very often that makes sense to me, and maybe you'll find it useful as well. All right. We're going to utilize a basic fact from algebra, which is simply that multiplying something by the number 1 does not change it. All right, that's so ridiculous. You knew that way back in grade school. It's not even really algebra, it's just arithmetic. And you might say, how is that at all useful? And the reason it's useful is that there are many ways to write the number 1. All right, you can write the number 1 as well, the numeral 1. But you can also write the number 1 as, say, 2 over 2. Or as 1 plus 1 over the square root of 4. In other words, there are many different ways to write it, and they might be convenient. This is not none of these are the simplest way to write it, only this one is obviously being one symbol is the least complicated way it could be, but there could be reasons that writing in other ways work. And for us, what we'll do is we'll take advantage of that to cancel out the things we don't like. For example, since 12 inches is the same as 1 foot, it must be true that 12 inches divided by 1 foot is equal to 1. They are the same thing, and anything divided by itself is 1. This allows us to convert, say, 1.8 feet, a number I pick randomly and comes from nowhere. If I said how many inches are there in 1.8 feet, you could convert it by saying 1.8 feet times our factor of 1. And then we say, well, feet over feet is 1. We can quote-unquote cancel that. And we'll have with 1.8 times 12, which is 21.6. So we get 21.6 inches. Now we have to be careful here. We get 21.6 inches, but we didn't really have that much precision. We only have 1, 2 figures here, and so we can only have 1, 2 figures at the end. So 1.8 feet converts to 22 inches. All right. Be careful with that. Our conversion factor is exact, right? Even though it's 12 inches over 1 foot, I don't really have only one sig fig in the bottom there. That conversion is exactly 1 to as many digits as I need. So only the 1.8 feet was controlling it. Historical aside, this is why you think that your normal body temperature is 98.6. Somebody in Europe who did the first study said, oh, the typical human being has a temperature of 37 degrees. And then when you convert 37 degrees Celsius, it becomes 98.6 Fahrenheit. But really, it should have been given as 99 Fahrenheit because you can't invent precision by conversion. And so that people are like, oh, I have a temperature of 98.8, I'm dying. People always tell you it's not really that important to be 98.6 because it wasn't measured to that precision to begin with. It should be around 99 degrees. And if you're much more than above or below that, then your temperature is a little bit off. All right, this is just pointless cartooning fun. That says, due to a unit conversion error, the portal to Narnia was opened at the Earth's core. I don't know if you know the Narnia books, but the Lion, the Witch, and the Wardrobe, you have a thing where you go to a different portal, and obviously, if you put it in the wrong place, you end up in trouble. A less goofy example of this, there have been several. Way back in the 70s, United States Congress said that we were going to move to the metric system. They mandated that federal agencies do, so NASA works in the metric system. It turns out the Jet Propulsion Laboratory, which was a thing at Caltech and was not officially a government agency, did not really get the memo, and they continued to work for a little while in British system. And in the 90s, there was a essentially conversion error because of that, where they didn't convert the thrust rocket was giving to the metric that the NASA program expected, and the Mars Global Surveyor missed Mars by about 60 miles, costing about $200 million, and was just lost forever. It's out in deep space now. There are cases where people get the conversion, they aren't paying attention to conversion factors, and they don't put enough fuel on airplanes. There's a famous story from the late 70s when the switchover was happening in Canada, actually, where they filled up on one side of the border, but were flying on the other side with pilots from the other side of the border, and so there was a conversion error in their head, and they took off with only about a quarter amount of fuel that they needed, and they had to make emergency landing. So it sounds very boring, but it is actually super important for the functioning of our society. All right, you can make this arbitrarily complex, and there are times that you might want to combine this, which is relatively straightforward. So here's sort of, for me, an extensive example based on the technique that I use. You want to convert 55 miles per hour to meters per second. So I start with 55 miles per hour, and I multiply that there were 1.6 kilometers per mile, and that eliminates my miles. So now my answer is in terms of kilometers per hour. I don't want that. I want meters, so I'll multiply by some number of meters, 1,000 meters in every kilometer, and that will get rid of the kilometers. So now I'm in meters per hour, but I don't want that either, so I'm also going to convert 1 hour is 60 minutes, which gets rid of the hours, and 60 minutes is 1 minute is 60 seconds. That gets rid of the minutes, and I'm left with meters per second, which is what I wanted. And then I just string all the other numbers together. I just take 55 times 1.6 times 1,000 divided by 60, and I get 24.44 meters per second. And then I recognize again I only had 2 digits to start, and so I should only have 2 digits at the end. So I have to go to only 24. So 55 miles per hour is basically 24 meters per second. All right, if you make an estimate of something with only one significant figure, we call that an order of magnitude estimate. Because remember that the order of magnitude for something was just the power of 10, and so we're saying how much times the power of 10 to within a factor of 10, essentially. The order of magnitude estimate is indicated by the symbol tilde, which indicates even less precision than the usual approximately equal symbol, which is sort of a curly or wavy equal sign. All right, and so we can say approximately 1 kilogram is approximately 2 pounds, or 1 meter per second is approximately 2 miles per hour. I do not recommend that you memorize this chart. You may, if that's the way you like to learn things, that's fine. I don't think it will be sufficiently useful. It's good to have a back of the envelope kind of idea, though. It's good to know that, for instance, a kilogram is about 2 pounds. So that if you get numbers for somebody's mass in this class, and it turns out that you find, oh, their mass is 1,580 kilograms, you're like, that's a lot, because that's about 900 pounds, and that's too much, so, or 750 pounds. So it's not bad to have a rough idea. I don't think you need to memorize it. In general, you won't need to do any conversions for the AP test. You won't do any conversions from British to metric or vice versa. We'll do a few in class, and when we do, I will give you the conversion across the boundary of the system. You're not expected to know any of the conversions between British systems and metric systems, but it's good to have a rough idea. All right, so if you want to estimate what your walking speed is, and you might say, well, I walk maybe in a mile, it might take me about 30 minutes to walk in a mile. Maybe, something like that. So if we say that that's a reasonable speed, then that speed would be something like 1 mile per half hour, or 2 miles an hour, as said here. And if we want meters per second, we'll then want to convert. Since we're just talking about orders of magnitude, we might take the conversion that 1 mile an hour is roughly half a meter per second. So we walk at roughly 1 meter per second, which is about right. It seems reasonable. The thing with order of magnitude estimates is that you want to check if you made them 10 times larger or 10 times smaller, do they become unreasonable? So I think that saying you walked a tenth of a meter per second, that's only a few inches per second. That doesn't seem reasonable. And if you walked 10 meters per second, that's pretty much Usain Bolt and the world records for 100-meter dash, which is around 11 meters per second. So your walking speed is probably not comparable to the dashing speed of the fastest person on the planet. So 1 meter per second seems about right. If you got an answer that was like 1.5 meters per second, that could be right too. Like, this is an order of magnitude estimate, and it could vary by roughly a factor of 3 in either way and still be entirely reasonable.